This video will discuss rate laws in chemical kinetics. So we'll look at our prototypical reaction here. Reactants A and B going to products C and D, each of them having a stoichiometric coefficient, nu A, nu B, nu C, nu D. We defined in the previous video the velocity of the reaction, or the rate of the reaction, V of t, equals 1 over the volume of the system times the derivative of the extent of reaction with respect to time, which is equal to the 1 over the stoichiometric coefficient times the derivative of the concentrations of our species with respect to time. It's negative if they are reactants and positive if they are products. As the reactants are consumed, dA dt is negative, so negative times negative is a positive velocity. And our products are produced, so their derivative over time is positive. Positive times a positive gives a positive rate of the reaction if our reaction is proceeding in a forward direction. Okay, so this video, we're going to introduce rate laws. So this tells us what is our rate of reaction in terms of the concentrations of our reactants. So V of t is equal to K times A of t to the power ma times B of t to the power mb for our reaction here, nu AA plus nu BB going to nu CC plus nu DD. All right, so what are the parts of this equation? In purple, I have the reaction rate, V of t. In yellow, I have what is called the rate constant, K. In blue, I have the concentration, or the molarity, of A and B, the number of moles per liter of each of those species. And then this power here in orange is what is called the order in A and B. So the powers here, MA and MB, those do not necessarily equal the stoichiometric coefficients nu A and nu B. In order to get these, what the value of these integers, usually integer coefficients are, we have to look at some experimental data and try to derive what that result is. It isn't just from the structure of the equation. So usually what we have to do is determine those empirically, and often these values end up becoming things like 0, 1, or 2. Although they are not necessarily integers. They can be other values as well. But most often we'll see integer values. Okay, so we would say that this reaction is mAth order in A. If it's 0, 1, or 2, 0th order, 1st order, or 2nd order. We say that the reaction is mbth order in B. Again, 0, 1st, or 2nd order in B, most often. And the reaction is Ma plus mbth order overall. So if we add up mA and mB, that gives us the overall order of the reaction, which can be 0, 1, 2, or even some other value. Okay, so the units on the rate of reaction is moles per liter per second, or molar per second. So the concentration of each of these species that show up is going to be mole per liter, or molar. So the units on the rate constant depends on the overall order in the reaction, Ma plus Mb. And if we have more reactants, there could be more reactants in there as well. Just whatever the total order of the reaction is depends on our units of the rate constant. Okay, so if we have a total order of 0, then whatever we have the rate constant units equal to, it needs to be whatever it is times the values over here equal the units on this side. So if the total order is 0, there's no other units over here, the rate constant just needs to be equal to the units of the reaction rate. It's molar per second. If it's first order, we already have a molar over here, so all we need to cancel it out is per second. If it's second order, we have a molar squared over here, so we have to cancel out one of those molars. So for second order reactions, our reaction rate constant is per molar per second. And other values would have other orders would have other values of units of K, just whatever you need to do such that the order, so molar to that power times K, gives you molar per second. So these are rate laws, and we'll now move forward looking at how we can determine these and some other things that this will tell us about our reaction.